I'm going to start talking about naming. Now, it will be a bit abstract in the beginning. Bear with me, because in the end, it will all make sense. I want to talk a bit about names, identifiers, and addresses. We'll talk about name resolution, DNS, okay, I mean in peer-to-peer, and also a bit about namespace implementation. That's actually where I will be talking about DNS. You were a DNS expert, right?
Well, I like it.
That like it, okay. That means you know more about DNS than I do. So I would, as soon as we start talking DNS, I would encourage you to correct me, supplement me, I don't care what, but if you have valuable information, I think it's important to share, okay? And this, by the way, holds for all of you. If there are there are always people in my class who know much more about a specific topic than I do. Let us know, okay? Because sometimes the gory details are more interesting than what I talk about. Okay, let's talk a bit about naming. Now, this is the abstract part. If you take a look at what naming is all about, it's something about this. You have these entities in a distributed process, and now entities can mean anything. They can be as concrete as a file. They can be a memory location. They can be a network address point. They can be a process, anything, okay? But you want to denote these things, and that's where the going gets tough. Because to operate on an entity, file, process, memory location, whatever, you have to access it at an access point. And the point is, pointing to an access point is really difficult, if not impossible. Have you ever thought about the access point of a memory location? You know, just try to imagine that you're inside a computer and you could say, there. And you try to point to that location. You can't do it. Have you ever thought about this? You simply cannot do it. Because when you start zooming in, your location goes away. Because it turns out that in the end it's just a bunch of electronics or whatever. So we do this differently. We always work on a higher abstract level, and what we use is an address. And we can talk about the memory location in terms of its address. And then the system will know what to do with this notion of an address, and will make sure that your stuff gets stored at that specific memory location, which has been identified by its address. And now we have two things. We have a name and we have an address. And that's what naming is about. How do I take a name in whatever form and transform it into an address? And to give you also a very concrete example of how this works in networking, how hard are IP addresses? They are extremely soft. You have to realize that an IP address is just a bunch of bytes, and that's it. Okay? But the internet knows what to do with an IP address. And in the end, what it does, it translates an IP address generally to a MAC address. Now, MAC addresses used to be very hard. Well, they kind of were uniquely associated with a MAC level, a data link device, I should say, an Ethernet card. But nowadays, you can change your MAC address if that's appropriate. To give you an idea, am I supposed to give you this idea? I'll give you this idea. So here at the VU, what we have are ports. If you want to hook up your computer to the network, and I have my computer hooked up to a research network, use a port, and that port has a unique association with a MAC address. So now you have a problem. If I change my computer, I have to go to the IT department and say, hey, I just switched on a new device with a different address, and now will take 24 hours before it can access the research network. So how do you solve this problem? Well, you take a router. You take a spoof. You spoof this thing. And you take a router, and you make sure that the router that you have can actually, that you can change the MAC address of that router. So now the IT department has an association with, actually, I don't know exactly which address. I have to write it up somewhere. with that port. So now if I just want to change something, I buy another router, and the only thing I need to make sure is that I can change the MAC address, and then I just insert another router. Hey, bingo. How hard is a MAC address? My God, it's just very, very soft, isn't it? And this goes on and on and on. So this is as soft as it gets. But naming is about taking a name and resolving it to an address. And after that, you know what to do. So what you're generally interested in is trying to find location-independent names. It's independent from the addresses of the access point offered by this entity. Okay, so if you have a multi-home server, just name that server, give it a name, and then, map it to different addresses as needed. Okay. That's about naming. We often work with identifiers, and identifiers are strange things. It's a name that has no meaning at all. In essence, it's just a random string, okay? And it's used actually only for comparison. You have to realize this. Now, for most of us, this seems pretty useless, but in fact, it's extremely valuable. Because if you really have a pure identifier, you actually say, I don't have to talk about that entity, I can just take its identifier, and that represents that whole entity. So what's an identifier? Every identifier refers to at most one entity. Yes, preferably so. You don't want to have this identifier say, well, it's that person and that person. That will be wrong. Every entity is referred to by at most one identifier. Preferably so, not strictly necessary. Depends a bit on your context. But you would like to have this one-on-one relationship between an identifier and the entity. And this is also an important one. An identifier always refers to the same entity, and this prohibits reusing an identifier. And we all know these examples from the newspapers where suddenly an identifier pops up because it has been reused, and the person to whom it belonged to actually died, but let's say that in the administrative system was not dead enough. So it was, the person who was assigned this new identifier was getting all kinds of stuff related to this very dead person. Now, an identifier doesn't have to be a pure name, okay? It may have content. That's a kind of a strange remark. How would you generate an identifier? How would you generate an identifier? It's a random bit string. What would be a really good identifier? How would, give me an identifier, I would say.
If it's random, you can just create a random string.
Well, how do I create a random string? If I would ask you, give me a really good identifier, what would you do?
OIDs that SNMP uses, those are good.
How do say that? Sorry.
There is actually an authority that decides which kind of.
Oh yes, of course. I don't want that. I want to have. Okay, I should have made my question more precise. I want to have a locally generated identifier for which I know pretty sure that no one else will have it.
Have a sequence where you choose a number, and that sequence will go on and on, or a hash algorithm that is based on time and other resources from that local computer.
Okay, that's a very good answer. So for example, take a hash function based on time. And you mentioned something very important, kind of other local properties of that computer, which is very good. It's IP address, size of memory, current processor speed, just a bunch of things that are kind of unique to that thing. Now, hash it. Hey, you're probably a very happy camper because nobody else has that same bit string. That's very good. When I mean it can have content, I'm even willing to accept that you don't even take the hash of it. Take time, IP address, current memory size, fill it into how many bytes you have. Very high probability that nobody else has that series of bits. The only thing is, I shouldn't rely on that content. So that's good about the hash function, that's really a one-way function. You take all this information, you generate a hash, going back into where it came from, that's pretty tough. So I like your example. Very good. But you see how you could do this. Okay? And there, you cannot preclude that anybody else would not have that same hash, but hey, chances are so small, good enough. Chances are so small that there are other problems that are bigger to worry about. That's something to remember in distributed systems. Yes?
Why do we need to be random? Why do we need to use the hash tree and not just use it?
Very good. You don't necessarily need to have that. Okay? But let me rephrase then what I just said. It appears to be a random bit string. If you just see this, you could say, oh, I don't know what it is. The only thing I can do is treat this thing as if it were a random bit string without any content.
So we can use just naming policies. For example, we use name of the room of the PC first, then something else, then my clone name.
Yeah, so you can take any well-known content, like you said, room name, building name, or all these type of things, you paste them together, and then in principle, you have something, but the crux is, do not interpret what you see. Interpret what you see. Treat those symbols as a series of random symbols. That's the most important thing. And that means that the only thing you can do is compare identifiers. Okay? Okay, now, where am I? Yes? Let's take a look at flat naming. And by the way, look at my slides, because within no time we'll be talking about peer-to-peer networks. Okay, so that's where you need to pay some attention. Okay, flat naming. Flat naming is like, here I have my identifier, and now I need to look up something. So I already gave this example. I have a key that represents a file. Where is its content? Okay, that key represents the file, and I got to look up the file. Looking up the file means where is it its access point. So I need to have a pointer back to the file. Hey, send your operations to that guy over there. So giving an essentially completely unstructured name, like an identifier, how can we locate its associated access point? That's the formal description. Now I'll be discussing some simple solutions, broadcasting, home-based approaches, distributed hash tables, that's your peer-to-peer stuff, your magnet links. Okay, after this you'll know how magnet links works, and the hierarchical location service. So the simple solution is you do broadcast. Who has it? Okay, and we all know that this is a well-known and well-deployed algorithm. It's called ARP. Okay, if you go to computer networks, you have your router in your local area network that gets this IP address intended for one of the nodes in that local area network, and when it starts, it doesn't know who has that address. It says, who has this address? And one of the nodes, hopefully only one of the nodes, sometimes when you have a misconfigure of your local area networks, there is this Microsoft thing that pops up, hey, you seem to have another guy who has this IP address as well. Okay, but it's all related to ARP. Who has this address? And there's this node, preferably one, and only one, who says, I have this address, and my MAC address is this. At that moment in time, the router can make the association between an IP address and a MAC address, remembers that association, and sends that thing off to that MAC address. Basically put it in a frame, says, this frame is intended for the computer with this MAC address. And then the other computers behave really nicely because they don't pick up this message. So the vulnerability is here, security, if you don't behave according to the protocol. Okay? But this will never scale beyond local area networks. You can't broadcast across the internet who has this IP address. It's not going to make anybody happy. Also very important, everybody has to listen to this request, who has this address. If you don't have that, you're not going to get an answer back, perhaps from the guy who's the owner of that address. So you have a scalability problem. Otherwise, works like hell. You can also have forwarding pointers. This is the Hans and Gretel story, and I don't think I'm going to repeat it, but in the end, I always say I'm never going to repeat it, and in the end, I always repeat it. So I'll promise not to repeat it, and I'm not quite sure whether I'll hold my promise. It's a very simple thing. You have an address associated with an entity, a file, a mobile agent, Okay, mobile agent is the easiest one, and the mobile agent moves us to another computer. And what you do is that in the place where you were, here comes Hans and Gretel. You drop a stone with some information. I'm over there. Okay, so you have this stone with I'm over there, and you walk over here, and then hey, you get contact. So if you're the what is it? I think the witch? No, it doesn't matter. If you're going to look for Hans, you're first pointed to the first place where he was, and then you find this stone. Says, okay, stone is the forwarding pointer. He's not here. He's over there, and you walk over to the place where Hans is. Okay, that's a forwarding pointer. And what I always say is, but now I can do this in a kind of context, and I'm even going to keep this recorded. So at universities, you have this group of people who want to make sure that we try to make money out of our ideas, okay? And they try to enforce us to submit patents. I'm generally opposed to this idea because I don't think universities are equipped for this kind of commercial behavior. I'm not supposed to say this, but I'm saying this anyway. And I'm sorry, I'm also a lefty, so people pay taxes, and I live by those taxes. So if I have an idea, whoopsa, I'm throwing it back, and I hope that there's some company who says, that's a nice idea, let me make some money out of this, good for you. And I'm really not supposed to say this, but I just said it. And why am I saying this? Because forwarding pointers have been patented. I mean, this is just stupid. This has been done years ago. And of course, you always have to write the patent in such a way that, it seems as if you could make money out of it, but as soon as you change it a bit, because this is a very sensible idea, then, hey, you're not going to get any money for it. So this is a patented concept. In the details, that is stupid to patent, but people have done this. Forwarding pointers have a problem, and this is where Hans and Gretel came in, because the first version was that Hans was using breadcrumbs. Dumb. Because you have birds, they pick up the breadcrumbs, and then the chain's broken, okay? And you have exactly the same thing with forwarding pointers. If you lose a forwarding pointer, then the whole trail will be lost, and you will not be able to find or locate the mobile agent associated with those forwarding pointers. Instead of you use stones, cobbles, something like that, birds don't like these things, and they tend to stay in place. Okay, so that's more robust. But you have to take care of this. Yes? The practical view on forwarding pointers... Oh, well, the thank you. Touché. The practical thing is that you need to make sure that if you have these chains, that they need to be robust. So if you just maintain your chain and you do not make sure that you have shortcuts or anything like that, then as soon as one of your computers, machines in that chain fails for a while, you will not be able to dereference to the mobile agent holding the actual IP address. Okay, that's the analogy.
But there's no solution for that.
Yes, there actually are solutions. What you need to do is to clean up your chains as quickly as possible. So what you see is that if you have a system of forwarding pointers, you actually don't have this on the slide. You actually have a garbage collection mechanism running in parallel with those chains. And what it tries to do is reduce those chains, not only for latency, but to have a subsystem where clients who are holding references to, say, somewhere in the middle of that chain have a backup such that if the dereferencing fails, that they can instantly go to somewhere else and then see what the current status of that chain is. That thing is, by the way, called a home server. I'll come to that in just a minute. Okay? So you have to have that, otherwise you'll have a very vulnerable system. Okay. So let's get to the home-based approaches, which is a very, very centralized solution. And for that reason, it's really not that fun. But my God, it works like hell. So let a home server keep track of where you are. And that home address is registered. I roughly explained this scheme a while ago. And it also registers the foreign address. So if I move to another location, I tell my home server I'm over here, and then essentially you get this scheme. Okay? Here's my client, here's my home address, and here I am somewhere in South Africa. And what happens is that if this client wants to contact me, what it first does, it sends a packet to the home server using the IP address that is associated with me. Now at the home server, two things happen. The home server takes my packet, and I'm explaining this at the application level, but you can implement this at the network level. It takes my IP packet, puts it as data in another IP packet, but now addressed to the location where I am, which is somewhere over here in South Africa. And actually what it does, it delivers that packet to a foreign agent, now in South Africa, who knows that I'm in that foreign agent's local network. Okay? So it can then unpack, unmarshal that packet, pick up the original packet that I, as a client, had sent, and now send it directly to me, this mobile user computer that is moving across the world. The interesting thing about the scheme is that to me as a client or to me as a receiver, it's very much transparent how my packet actually crossed the whole world. The second thing, I'll come to you in just a minute, the second thing that the home server does is tell the client he's not here, he's over there. And over there means he provides the address of the foreign agent. So from that moment on, my system software, and yes, it can be middleware, will take all the packets that come in from the application, put it into an IP packet with now the address of the foreign agent, and forward directly to the foreign agent. Okay? Completely transparent to the application. Well, that's a very good question. So if the client is setting up two TCP connections to me as a recipient, would you go through this scheme twice? Would send directly to the foreign agent, also for the second TCP connection? That would be a good solution. Yes, but that's clear. If you don't have this association or you're not going to make use of it, you would go back to the home server. There's no optimal solution. I like that answer actually a lot. Why do you say this? There's a trade-off. The trade-off is you'll be moving all the time. So you have another problem, namely to make sure that the binding that you have between the IP address that was originally assigned to me and the address of the foreign agent, that binding is valid for a while. So when you set up the second TCP connection, you have to make sure that binding is still okay. Let's make that assumption. Okay? It's still a trade-off, not necessarily in terms of performance, but perhaps in terms of simplicity versus performance. So you could follow a very stupid approach and tell any TCP setup piece of software, don't think that there is a cache, which means less code in that part, right? Just do what you would normally do, boff to the home, and then you get something back. You would have a full separation, could have a full separation of setting up and maintaining TCP connections and actually forwarding and tunneling packets. Okay? I don't know which one is better. Sometimes splitting things apart may simplify things, but hey, it will cost you performance, but it will gain on simplicity. Now, in this particular example, I can imagine that it's very easy to actually maintain a cache because you have a specific layering system in this whole thing, and then you almost always have to go through the cache. But it's the idea that counts. So that was a very good question. But you see the trade-off? So there is indeed no single optimal solution. It all depends. Good question. Okay. Now, there's a variation on this scheme, which is actually used in telephony networks. They use the home-based approach. So, you know, if you and I would go to a conference in Germany and we would use our phones, we would first have to phone home, and that's the reason why we get billed. Okay? We will not be making use of the local thing. Now, technically, what you can do is you can say, well, are you close by? And that's a two-tiered scheme. you first check with a local registry. Well, I'm looking at this phone number, and is the person that I'm looking for, by coincidence, is it in the same cell or region as I am? If not, okay, I'll go home, okay, and then check out where this guy is. So that's basically keep track of visiting entities and then check the local visitor registry, register first. And then you go back to the home locations. Okay. I don't really know how effective this actually is. I really don't know. So I don't have an opinion on this. The only thing I can come up with is that they actually came up with this scheme because it works. So there must be a reason. On the other hand, I gave you this example of Globule during the first class, where you see that there's this hard-coded policy of web caching. And when I showed you the statistics on if you would just take a boring site like the VU, would that caching policy be used? And the answer was no. So don't rely on oh, this is nasty. Don't rely on natural intelligence from people who would hard code policies into their systems, okay? They were just guessing, but they may also be right. You just don't know. Okay, so there are some obvious problems with the home-based approach. The home address has to be supported for the entity's lifetime. That means if you permanently move to South Africa, you still have a guy over there in New York forwarding your packets. So that means that the home address is fixed, unnecessary burden when the entity permanently moves. And very poor geographical scalability. Okay. I used to say, I still say this, but it really all depends. The internet is so fast, so it really depends on what you want to do. How can you solve the permanent move problem? So I permanently moved to South Africa, and you're looking for me. Well, that's a problem, because you have my old address. You've never really contacted me, but I am known by my address. I could say that my address is my identity. Okay? Now you have a problem because I just changed identity. So you just gave, I always say this, also, you gave the ultimate solution, what computer scientists always do. They never solve your problem, they just introduce another level of indirection, okay? So I don't know what the solution is to your problem, but I can invent great tools that will help you solve your problem. That's what computer science is all about. But the answer is actually correct. What you're saying, and this is the fundament of your answer, saying, listen, that home server has a certain stability. So if you move permanently, then, so what is permanently? Maybe a couple of years. But basically what you're saying, don't make that home server that permanent. Rely on something that you really only occasionally have to go to really check if that home server is there still in place. And that's what you're saying. And you call it DNS, but it could be anything else. A well-known place that you hardly ever go to, that you don't worry about when it comes to scalability. And you say, I really don't know where he's up to now. Can you please tell me? And then you'll get back the address of my current home server, and that server will help you trace me for at least another couple of months or something like that. Okay. Everybody awake? Okay, here we go. We're going to talk about distributed hash tables. Magnet links, okay. Importance, these slides are more clear and complete than what's in the book, okay? And depending on the printing, if you have an old printing of the book, you really have wrong information. And if you have a more recent printing, you will have correct information, but there's still some information missing. So I would advise you to first study these slides and then go back to the book. But the slides should be enough to understand the principle. Okay, here we go. And it's fun. And it's really fun. This is, in essence, how, magnet links, yes, but also in Amazon, okay? Peer-to-peer networks, structured peer-to-peer networks are used for real in all kinds of organizations, and this is basically how they work, with many, many, many variations on this theme. But this is the simplest peer-to-peer system to explain. And for those who took a class on, did I explain that actually? the chord ring and graph theory? I may have discussed it, and I discussed it to skip it at a certain point. Okay, so I'll be explaining it again, but I think it's cool. Okay, so what you do is you organize your distributed system in a logical ring. This 10,000 nodes are just in a ring, and that's it. Okay, that's now my overlay structure, almost. And every node is assigned a random m-bit identifier. M is typically 128, 160. Huge. Okay? It's really huge. You can do a lot with 128 bits. Every entity, very important, file, let's stick to files. And every time I use the word entity, I mean a file. Every file is assigned a unique m-bit key. Also M. Okay? And from the same space as where you drew your identifier from. This is actually very important. Because I'll be using keys and identifier interchangeably. I'll use the keys to route towards a specific node having an identifier. So they come from the same space. This is also important. An entity with a key k falls under the jurisdiction of a node with the smallest ID greater or equal to k. It's called a successor. I'm now taking over the terminology from the chord system. There's one snag. Note that the successor of, if you have a node x, identifier x, and you have a file with key x, then the successor of x is x. That's the confusing part. It's not x plus 1, okay, or x plus whatever. Successor of x is x, if you have that match. And what you then do is try to find your stuff, which has been identified by a key, by routing through this logical ring. And an obvious non-solution is that you let a node with ID, keep track of its successor ID and then start a linear search through the ring. It's not going to fly. And I hope that's clear to everyone. This will only fly in the main memory of a modern computer. It will not fly over the network because if you have 10,000 nodes in your peer-to-peer network, that means that on average you will have to do 5,000 hops and nobody's going to be happy. Okay? And you can reduce that by having a parallel search like this, and that means that your average will be reduced to 2,500. It's not going to make anybody happy. I know of no system where a search in the internet will survive 2,500 hops. Something will go wrong, okay? Apart from the fact it's going to take you ages. You let every node maintain what is known as a finger table. And the concept of a finger table is actually very important. Now see if you can understand what's going on over here. So I have a node P. When I talk about P, that means that that node has identifier P. Okay, we're all talking about numbers here. Has a finger table with at most m entries. M was the number of bits I was taking for the identifier space. Okay? And what I do is, I store in the ith entry, and I start counting from 1, so the first, the second, the third entry. I store the successor of p plus 2i minus 1, 2 to the power I minus 1. Now look what I'm doing over here. This is a crucial observation here. The finger table of node P, its ith entry, points to the first node succeeding P by at least 2 to the power I minus 1. Okay? If I simplify this a bit, I'm saying what I'm saying is the following. I'm going to divide my ring into slices. Okay, I start with slicing it up in 2. And what I want is to have a pointer to somebody in that other half. That's my first concern. That's my first entry, far away. Or you could say first entry, my last entry actually, far away, on the other half, the other side of the world. I don't know about that, what's happening. I want to concentrate on my part of the world. My part of the world is my slice, my half of the slice. Okay? This is the concept. And what I do is, in my half of the slice, I slice it up in 2 quarters. 1 quarter over there where I don't live, and the quarter where I do live. And what I do is, I maintain a pointer to that quarter over there. Okay, the quartz slice over there. So watch it. I now have 2 pointers. Way over there on the other side of the ring. Oh yeah, and by the way, on my part of the ring, over there in that slice. Somewhere in that quarter. I don't care where it is, it's just far away. Now let me concentrate on my part of the slice. Maybe I should start drawing something on the board. Sorry I can't record this, but you'll get the picture. This is an interesting piece of chalk. If you come to my room and I use the blackboard, and Claudio knows this, the pieces of chalk don't have this size. They are this small, and I haven't replaced them yet. Okay, so here I am. I'm this node over here. And what I'm saying is I'm going to chop up the world in 2. Whoops. My half, their half. Okay? And let me just give a pointer to somebody over there. I don't care who. Your problem. Your problem. Okay? Let me concentrate on what's going on in this half. Oh, maybe my drawing is not entirely correct. Doesn't matter. I'm going to chop this up in 2 parts because that's my world. Well, what's really my world is this part. So, hey, give me the pointer to somebody over there because, hey, it's kind of within my city, other part of the city. And now you get the picture. I live in this part of the world. I'm going to slice it up in 2 again. And I'm going to say, well, give me a pointer to this part. Hey, close by, but far away, not any of my concern. And there we go again. I slice it up again. I slice it up again. Okay? And this goes on and on and on. And what I will be doing in the end is indeed maintaining pointers to the first node succeeding me by at least this distance. Close by, a power 2 further down the road, another power 2 further down the road, etc., until I'm on the other side of the ring. And I couldn't care less who's going to handle that on the other side of the ring. And this is why this whole thing will become efficient. Because as soon as I get something, I'll go into the details in just a minute. If I get something that is really on the other side of the ring, hey, I throw it over the fence. Okay? And now comes the important thing. It lands over here on the other side of the fence, and somebody says, hey, that's my half. Let me see if it's in my quarter or in somebody else's quarter. And if you're in tough luck, it's in that somebody else's quarter. Good. Throw it over the fence again, but not back. Okay? So you're in this slice, this half, and it's going to stay there. And you throw it over to this other quarter. Good. And now I'm talking about the worst case scenario. So now it's suddenly somebody else's problem. But the search space has been reduced to a quarter of their whole ring. Good, you slice it up again. The worst case is that it's not in your 8th part, but in somebody else's 8th part. Good, you hand it over. Do you see that within a logarithmic number of steps, you actually get to where you should be? It's on the other half, the quarter, the 8th, the 16th, 32nd, etc., 32nd, etc. That's the principle. And you formalize this like this. Yes? No. So now let's get into the details. This is the principle. So this is what you should keep in mind. This is the metaphor of chopping up your search space in a exponentially decreasing number of, in exponentially decreasing sizes, and that will lead to a logarithmic number of steps through the ring. And that's how it becomes efficient. Don't forget, I'm trying to get rid of it's already been a long day. It's not done yet either. So don't forget that I want to avoid, this linear search over the ring because that's going to take me 5,000 hops. I can't afford that. Within a logarithmic number of steps, I'm talking about 5 hops. Now that's doable, even with 10,000 nodes. Got it? Okay. Hold your horses. Okay. So let's zoom into the details. I'm going to skip the break. When I look at your faces, I'm looking at people like, tell us how this works. Let me tell you. But I promise I will stop way before 5 o'clock, okay? So bear with me. I'm sorry about this. And pay attention because it is important. And once you do understand it, it's not too bad, okay? Okay, here it goes. So to look, now I'm a node, I have to look up a key K, okay? And apply the following algorithm. I look up the key K, I'm node P, and I forward the request to the index J satisfying this inequality. Q is the finger table, is the node that I have stored in my finger table whose identifier is less or equal to K, but K is less than the next one, than the next entry. Okay? And I will get to this bullet in just a minute. What is the principle? It's not your random number. The principle is that it's over there. Okay? And what I said is that if I'm a node with identifier ID, I am responsible for, I got to get this right, I'm responsible for files who have a key K where K is just a bit bigger than mine. Okay, did I say that correctly? I got to get this right. With the smallest identifier just over K. That's the one who's responsible for it. Okay, yeah. So I said it wrong, okay? Let me correct. My identifier is just a bit bigger than K. That's the ones I'm responsible for. It's important that I get this right. I'm a node with identifier X. I'm responsible for files who have a key value just smaller than mine. That's the reason why I said they come from the same space. No, they have exactly, so what I'm using, my keys for my files are 128-bit identifiers. My identifier for a node is also a 128-bit identifier. Okay? So that means I can compare them to each other. And I can interpret them as numbers. Oh, sorry, yeah, I can interpret them as numbers. And I'm a node X, and I'm responsible for files with a key K that is just smaller than my own identifier. Okay, that's the general rule. Now what this rule says over here is if I have this request, I have to hand it out to somebody else, but I shouldn't be overshooting. I shouldn't be handing it out to a node who has an identifier larger than K, because I may have missed somebody just before this identifier who is actually responsible for that K. So what I need to do, I need to push this thing as far as I can to a node I know who is just before K. Are you with me? Does everybody understand what I'm saying here? I got to get as close as possible to K from how do you say this in English? From the onderkant. From underneath, okay? From the bottom, from lower than K. Because if I move to a node that is already beyond K, I may be missing nodes that sit between K and the node that I just handed out the request. And that means I just overshot myself. That's the principle. Yes?
So you're saying throw it in a smaller piece of the pie than in a larger?
In a way, yes. I'm saying throw it into the smallest piece of the pie possible, then overthrow it to the larger one. Yeah, that's I think a correct interpretation. I personally like the interpretation, try to get as close to K as you can, but don't overshoot it. And that don't overshoot, that is really in this formula. Try to get to the node who is just as close as possible to K that I know of, okay? But not the one that has an identifier beyond K, because then I may be overshooting. You first.
Why is serving and not a leaf-based binary search tree?
Why is...
Why is serving and not a binary search
I like this question. Why this hurdle and not a binary search tree?
Leaf-based binary search.
You know what this is?
It's the same thing.
It's a binary search tree. But there's only one big difference. It's my binary search tree. Okay? And it's also a very specific binary search tree because it travels the ring in one way. So your question could be, couldn't you invent a system where you can have a true binary search tree and that you could go both ways? And the answer is yes, you can. But I like the analogy, this is very close to a binary search tree. But you have to realize my binary search tree is now implemented in a fully decentralized fashion. So there are some nasty things here. And if you would ask me, the guys who invented this, by the way, this comes from MIT, from Franz Kasuch, who was once a PhD student of Andy Tannenbaum, and Franz Kasuch is considered as the computer systems guy, full stop. I wouldn't say something, but in our field. I bet you that he was thinking about binary search trees. And he was thinking, how do I implement a binary search tree across the internet? Bingo. You had a question.
Yeah, I'm still not getting as close to K as possible and the sort of binary search tree.
Okay, watch out. What you need to realize is that these guys over here, these entries, point to larger, increasing spaces, right? That means that what this guy represents is a space that is larger than what this guy represents. And I haven't told you how you found those nodes. And what I'm saying is that because of this formula, this guy represents a larger space. Now, why is that important? Because if I find a key that is really far away from me, what I do is I throw it really over the fence far away from me, as far as possible, maybe even in the other half, which is then good enough. That's what I'm trying to say. So you gotta realize two things. This thing would also work if I would have just my logical ring and do a linear search, right? And I would have pointers, random pointers, not according to this principle, random pointers in the ring. I would say, okay, I have my random pointers to other nodes in the ring. By magic, I found them. Let me just throw it as far as possible, as far as I know, close to K. And then, it's that guy's problem. In fact, that could work. But then, it's not necessarily efficient. And what I'm now doing is that I didn't just take random pointers to nodes in the rings, or random nodes. I carefully selected them. You're responsible for that part. You're responsible for that part. And the parts that they're responsible for differ in size. So I can be really crude saying, oh my God, this is on the other side of the world, not my show, that guy's show over there. Knowing that it will stay there. The search will be confined to that piece of the space. If it's in another quarter, say, okay, my space, but at that part. I know now the search is going to be confined to that quarter. That's where I get the efficiency. And that's the analogy with the binary search tree. Got it? Yes?
So each time this finger table has to be updated when the new ring is from the other one.
I haven't even talked about the updating of the finger tables. And actually, I'm not going to do that, because that's really where the algorithm turns nasty. I'll give a hint on how you can do this. Okay, so far so clear? I think you need to understand how it really works. So these gory details. More important is that you understand the principle. Or equally important, I should say. Yes?
Are you still going to explain how we actually get that?
Yeah. Sure. Okay, there's one subtle thing. If you have a key that is between yourself and your first entry, then you also forward it to this first entry. Okay? That means you're not responsible, but in principle, your neighbor, so to say. Okay. Here's an example coming to your system. Okay. Let's follow the red one. what I have, let's first take a look at some of these finger tables. Okay, this is an example that I think also I have in the book. Let's take a look at node 4. It has 5 entries because I'm looking at a system, a ring, where m is 5. So that's the reason why you see 32 nodes over here. Okay, and by the way, I start by 0, but I do that for counting. The entries here, they start always with 1. Okay, but I otherwise work in a modulo 32 system. That's the only thing I just skipped. Okay, let's take a look at these entries in this finger table. What I'm drawing over here is the entire identifier space. So in principle, there should be 2 to the power 128 nodes here. If I would use 128 bits, I'm just using 5. So I have 2 to the power 5, 32 nodes. These gray nodes are the real system. Okay? The other ones simply don't exist. They're not there. Now what I'm saying is that if you have a file with key 2, then node 4 is responsible for storing that file. Okay? Likewise, if you have a file with key 23, then node 26 is the one, is that 26? 28, sorry, is the one that is responsible for that. Okay? It will store that file. Okay, now let's first take a look at this finger table. The entry in the table is the successor of p plus 2 to the power I minus 1. P in this case is 4, okay? I is 1, so I'm looking at the successor of 4 plus 2 to the power 0, the successor of 5, which is 9. So I take this number 5 in this case. It says, who's responsible for 5? Ah, that's 9. In this example, because 9 is the real node over there. Got it? Okay. Next one, same thing. I take a look at the node who is responsible for the successor of 4 plus 2 to the power 2 minus 1. 4 plus 2 is 6. That's 9 again. Got it? The same thing for 3. Let's take a look at this one. Who's responsible for the successor of 4? That's me. Plus 2 to the power 4 minus 1, that's 3. That's 4 plus 8 is 12. Who's responsible for 12? That's 14. Okay, 12 is over here. 14 is responsible for 12. So the general rule is this node is responsible for all these keys. This node is responsible for all these keys, etc., etc. Are you all with me? Say yes or no. If it's no, that's totally reasonable. 1 is responsible for 31. That's where the modular arithmetic, which I just skipped over, but I'm doing everything in modulo 32. Which is, by the way, very important to keep in mind. If I ask questions about this, there's always one version which will use the modulo 32, whatever I use in my example, and half of you will get it wrong. Okay, so let's watch out for that one. Okay, let's look up key is 12 from node 28, applying the algorithm that we just had. Okay, yes?
How do you know your success in the network? Because for the first finger table, you pointed to 9. How do you know it's 9?
I'll get to that in just a minute. Let's assume now that the peer-to-peer network is in place. Okay? And no security issues, no misbehaving nodes, everybody's up and running, no lost messages, nothing of it. It's a completely false distributed system because I'm violating every fundamental assumption that I mentioned during the first class, okay? But just to keep it simple. Okay, let's look up, is that actually a good one? Yeah, let's look up 12 from node 28. Okay, so what this means is there's a client out there that contacted 28, says, hey, where's file with key 12? What happens? And now pretend you're a computer. Yes?
28 looks at 12, says 12 is smaller than 14 and larger than 4.
That's it?
So I go to 4.
So I go to 4. It says, here 4, I got a request for resolving key is 12. I don't know who's responsible for key is 12, or K is 12. So the request comes to 4. 4 is also a computer, so it doesn't think, there's nothing intelligent, it applies an algorithm. What does it do?
The same thing.
It does the same thing. Tell me what the same thing is.
Checks whether where 12 should be in between the.
Okay, so
the finger and
tell me when to stop.
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 One more up.
Okay, so what 12 is between 9 and 14, forwards it to 9. Okay, deck, forwards it to 11. And now? So we have node 11 over here.
Just the neighbor.
And then?
Just the neighbor. Send to the neighbor. It was the special case.
It was the special case. That's what I wanted to hear. Okay, so if we go back to the previous slide, we have I'm 11. I'm looking at key is 12. And the first successor that I have was, I think it was 14. So yes, I forward to 14. And yes, that happens to be the node, and not by coincidence anymore, who is responsible for key is 12. Got it? One more? This is very simple. I mean, I could take the red one, but you do the red one at home. Okay? You should be proficient in this. Okay? That means that, and just to make you nervous, what I do is I have a Python program, and I just type in some parameters, and it gives me a chord ring, and then I say, okay, look up this key, and I get the answer. And the program is correct. That means that I can I think it is. I can generate any chord ring. I throw in some queries. I take a look. Oh, this is an interesting path, and now I have a question for my exam. Okay, so be prepared. You know what you could do? You could write this program yourself. Bring it to the exam. I could also give you the program. The interesting thing is, I wrote it in Python, it's actually very simple. It's a one-pager. And I mention this specifically because it illustrates how simple the algorithm is. And everybody's executing this algorithm. Okay? Okay. Bear with me just a few more minutes, and then what's the last one? Yeah, I promise, we're almost done for today. How do you maintain the finger tables? So let's get back to a question. I think you mentioned, no, somebody mentioned, I don't know, I think it was you? Okay. So let's keep security, okay? I want to say something about security in just a minute. But let's start letting nodes leave. So 4 leaves, it goes. But how do you let a node leave?
It tells the successor it's leaving.
So it tells the successor it leaves, and then what? So it tells 9, hi, bye, I'm gone. Good for you. Okay.
I think it needs to go back to the predecessor. Because that one needs to know that it has to go to 9.
So it has to go to 9. So this guy is gone, okay? So there's now something fishy going on.
Yeah, one needs to go straight to 9 and not to 4.
Yeah, so you mean 9 needs to, say this again? 9 needs to go to, no?
No, 1 needs to know that 4 isn't there anymore.
Okay, so let's assume that 4 has knowledge of its predecessor and its successor, and is very kind, says, hi guys, I'm gone. Okay, good, gone.
You cannot rely on this. You cannot have a system in which you rely that somebody will go when it goes away.
It's gone.
Exactly.
Collapses.
Exactly.
Good,
It
gone.
won't announce.
Okay, it won't announce. Okay. Shit. Let's first assume it will. And I'll give you a proper answer in just a minute. Okay, so this guy just tells, okay, 1 I'm gone, hey 9 I'm gone. Will you take over? That's it. Okay, I got a problem. I still got a problem now.
Of 20 and 18 should also be.
So that's the nasty part. Okay, and that's the problem you're addressing as well. So the nasty part is, my God, who knows about me? You don't know, right? That's really the problem. How does 4 know that 28 has a pointer to him? And now comes the crucial part. Should it know? No, of course not. I mean, you will want to have things decoupled, right? So 4 says, okay, 1, 9, hey guys, I'm gone. And let's take it from there. So now we have rubbish in finger tables, right? Let's see how bad that is. So 28 gets this request. Oh, you send it off to 4. 4. Who's 4? I don't know. Oh, 4 is not there? Bzz. So what does it then do? Which is according to... No. It's 1. It's 1. Oh, I thought 4 was okay. 4 to 1. It's still, it's not clear whether this is the right one, but maybe you can discover in due time, because nodes may come and go. Okay, so for now, no 4 left. Told 1. Okay, 28 discovers no 4. Okay, who then? Oh, 1. 1's my best choice. Let me hand it over to 1. It's just not optimal. Okay, but it will get there. 1 knows that 4 is not there. Okay, well 9. And then there's this guy 18 over there. So it gets 12. 12 is now, oh, these guys are not there. So, oh yeah, I have to forward it to 9. So it will just forward the request to 9. Hey, we're back en route. Okay, this is, and I'm glad that this example worked because I didn't prepare myself. At least not for this example. But the take-home message is, this is actually a very robust scheme. So when something goes wrong, your finger tables may no longer be correct, but it's not that important. It will still work, but it will not be optimal. Okay? So now you see how you can join a network. What you do is you say, hi, node 4 is going to come back into the network. I'm node 4. And node 4 contacts, I don't know, an arbitrary one, 21. So he flipped a coin and said, hey, 4, okay? Because a random identifier says, I want to join you guys. Okay, let's see who's responsible for you. Which is 9. And 9 says, back again? Good. You will be my predecessor. So here's a pointer. Will you please point to me? Oh, by the way, I had 1 as my predecessor, so I'll give you that information. If you contact 1, you're in the ring. You have no finger tables. You have an empty finger table. No worries about that. I'll give you some information that is of interest to you, because this is at least the stuff that I was responsible for, but now you're responsible for that. Namely, all the files who have a key that is between 1 and 4. Here they are. Good. Okay? And by the way, will you please contact some other guys over here and try to see who's also on the ring, so that you can gradually fill up your finger tables. Now here comes the interesting thing. Your finger tables, I just argued, need not be accurate. Okay? You can have, this is the complexity in core, you can have a rather intricate algorithm that will give you pretty good finger tables the instant that you actually join the ring. But what you also do is gossip. Okay, you can have a completely separate system that says, let's just gossip. And now, not just gossip and then just do an exchange. No, you apply a gossip algorithm with some greediness. Because you know what is needed in your entries, in your finger tables, right? So you just start collecting knowledge on who's out there in your ring. And what you do is, you start with reasonable identifiers in your finger table, but the moment you get a better identifier, and let me make this concrete. Let's say 4 had discovered 11, and has not discovered 9. Possible with the joint algorithm I just had, but ignore that, right? So it plays in all kinds of entry tables because, hey, that's the only thing it knows. And then at a certain point, it discovers 9 is also part of the ring. Oh, good. You're a better candidate for my entry 1 and 2 and 3. I'll put you there, and I'll throw. So what you can see, hopefully, is that gradually the finger table will actually get much better. And what we prove is that even with just a few number of rounds, the tables will be optimal. Now, the interesting thing about these peer-to-peer systems is they tolerate sloppy finger tables. Sloppy, I mean that, hey, your request may actually be running too many hundreds, but only for a very short while, and that's good enough. Got it? Cool, right? We'll see. Oh, there was one more question here.
When 4 died, how did you when 4 died, how did you decide one to
Oh, because 4 had a predecessor to 1. Yeah. So the case is where 4 has a pointer to its predecessor and successor. So it's from those, and that will help a lot. It's necessary to have at least your. What? Only 1 is necessary. More help. Oh! Hold it. I have to give a proper answer to your question. So we will now not announce that it's a ring. So what you do in a system where peer-to-peer system that stores files, you replicate files. So you do not make a single node responsible for files because then you just lost files. So when you look up a file, one limitation is that on the way back, when you just figure out who's responsible for that file, you will have touched nodes. They can dynamically take copies of that file, and now suddenly you're on tape. Okay? And then anticipating our discussion for next week, because tomorrow we don't have a class, what you can do is you can optimize also. If you know that your files are replicated, then on the way towards that node, you may bump into a node that already has that file. In fact, if you know more nodes than just a specific interval, you could say, and now network proximity to account, let me go to that node because that one is also closer by. And that would improve the latency. So the tolerance part should now have been answered. Got it? Next week, Tuesday. Okay? No tomorrow.